Mental strength and confidence are not abstract traits. They are functions of specific neural circuits that can be understood, trained, and optimized. At the core of this system is the dynamic interplay between the prefrontal cortex and the amygdala, two regions that govern how we interpret and respond to stress. The prefrontal cortex, located in the anterior portion of the frontal lobe, is the executive hub of the brain. It is involved in higher-order processes such as planning, impulse control, cognitive flexibility, and emotional regulation. In contrast, the amygdala is a subcortical structure critical for detecting threats and generating emotional responses, particularly those related to fear and anxiety. Under acute stress, the amygdala initiates a cascade of physiological responses designed for rapid reaction, often referred to as the fight or flight response. While this response is adaptive in life-threatening situations, its chronic or inappropriate activation can erode confidence and impair decision-making. Confidence emerges when the prefrontal cortex exerts top-down regulation over the amygdala. This regulatory control is essential for reframing uncertainty, not as a threat but as a challenge. It allows for calm, focused action in the presence of pressure. This cortical control is not fixed. It is subject to change through a mechanism known as experience-dependent neuroplasticity, the brain's capacity to rewire itself based on repeated behavior and thought patterns. By repeatedly engaging in tasks that involve stress and learning to manage the associated arousal, individuals reinforce the neural pathways that support resilience and confidence. Dopamine, a neuromodulator associated with motivation and goal-directed behavior, is also heavily involved in this process. When individuals confront a difficult situation and persist through it, the brain releases dopamine, reinforcing the perception that challenge is linked to positive outcomes. This dopaminergic feedback loop strengthens the neural circuits responsible for effort, motivation, and reward anticipation. Additionally, the locus coeruleus, which distributes norepinephrine across the brain, increases alertness and enhances cognitive performance under stress. However, this system only promotes optimal functioning when the prefrontal cortex remains active and engaged. Developing mental strength and confidence involves more than mindset. It requires training the nervous system to remain regulated under conditions of challenge. One of the most effective ways to accomplish this is through controlled exposure to physiological stress, particularly in the form of deliberate cold exposure. This practice involves brief, intentional exposure to cold environments, such as cold water immersion or cold showers, which elicits a well-characterized activation of the sympathetic nervous system. Upon cold exposure, the body initiates a rapid stress response, marked by increased release of norepinephrine and epinephrine from the adrenal medulla and locus coeruleus. These catecholamines elevate heart rate, sharpen alertness, and prime the brain and body for action. Importantly, this stressor is non-damaging and time-limited, allowing the brain to experience the physiological intensity of stress without the psychological consequences of trauma or burnout. In doing so, it becomes a powerful training stimulus for enhancing stress tolerance and cognitive control. Crucially, sustained exposure to cold, when done voluntarily and with proper safety parameters, requires top-down engagement from the prefrontal cortex to override the innate impulse to withdraw. This voluntary override strengthens corticolimbic pathways involved in self-regulation, executive control, and emotional resilience. Repeated exposures reinforce the capacity of the brain to remain engaged during high arousal states, effectively recalibrating threat perception and building adaptive stress responses. Moreover, cold exposure has been shown to significantly increase baseline dopamine levels and sustain them over time. This dopaminergic shift enhances motivation, focus, and goal-directed behavior, key components of mental resilience. Unlike transient dopamine spikes associated with reward-seeking behavior, The increase following cold exposure unfolds gradually and persists, contributing to improved baseline mood and cognitive performance. In essence, controlled cold stress serves as a neurobiological training ground, allowing individuals to experience arousal states while cultivating the capacity to remain calm, focused, and in control. The development of mental strength and confidence is deeply tied to the brain's capacity for neuroplasticity, the ability to rewire itself in response to experience. Importantly, this plasticity is not limited to external interactions with the environment. It can be initiated and directed internally through structured cognitive practices. Among the most robust and replicable of these is visualization, or mental rehearsal. Far from being a passive or purely motivational exercise, visualization engages specific neural networks responsible for motor execution, cognitive control, and affect regulation. Repeated mental simulation of task execution or stress navigation builds functional connectivity across these regions, strengthening the underlying circuits required for real-world performance. Neuroimaging studies have shown that when individuals vividly visualize themselves performing a specific task, particularly under conditions of stress or high demand, there is significant activation in the premotor cortex, supplementary motor area, and dorsolateral prefrontal cortex. These regions are also engaged during actual task execution. This neural overlap is the foundation of self-directed neuroplasticity, the deliberate reshaping of brain networks through intentional mental focus. When visualization is repeated consistently, particularly when paired with interoceptive awareness such as controlled breathing, the brain treats the rehearsal as meaningful learning. This process facilitates more rapid and stable synaptic potentiation, ultimately improving behavioral outcomes under pressure. Visualization also serves a predictive regulatory function by engaging anticipatory mechanisms in the prefrontal limbic circuitry. When an individual rehearses staying composed and effective in the face of potential stressors, the brain learns to preemptively downregulate limbic activity, particularly in the amygdala, which is responsible for initiating emotional reactivity. This feed-forward adaptation enhances emotional resilience by reducing the amplitude and duration of stress responses before they fully manifest. Over time, the repetition of such cognitive simulations reshapes threat perception and cultivates a more stable internal framework for confidence. This approach not only enhances performance readiness, but also reinforces a sense of agency, as individuals experience direct evidence of their capacity to influence internal brain states through structured mental practice. The neurobiological substrates of mental resilience and self-confidence are highly sensitive to the body's underlying physiological state. Core regulatory processes such as sleep architecture, circadian alignment, and autonomic nervous system balance form the foundation of cognitive stability and emotional regulation. Without optimization of these basic systems, higher cognitive functions, such as stress modulation, attentional control, and adaptive decision-making, are inherently compromised. This underscores the central role of physiological self-regulation in the cultivation of mental strength. Sleep serves as the brain's primary mechanism for neural restoration and synaptic recalibration. During slow wave stages of non-REM sleep, large-scale cortical oscillations facilitate the downselection of synaptic connections, a process critical for maintaining neural efficiency and cognitive flexibility. Equally important, rapid eye movement REM sleep supports the reorganization of emotional memory networks in a neuromodulatory environment characterized by low noradrenergic tone and elevated acetylcholine. This allows the brain to reprocess emotionally salient experiences with reduced reactivity, thereby enhancing future emotional resilience. Chronic sleep restriction, even at subclinical levels, has been shown to elevate amygdalar responsivity while impairing prefrontal regulatory input, leading to diminished cognitive control and increased vulnerability to stress. Equally essential is the regulation of circadian biology via exposure to natural light. Morning sunlight, when absorbed through retinal melanopsin-containing ganglion cells, activates the suprachiasmatic nucleus acin of the hypothalamus. This central circadian oscillator coordinates downstream hormonal rhythms, including the timed release of cortisol, dopamine, and melatonin. Light exposure within the first 2 hours of waking is particularly effective in phase, locking these systems, enhancing wakefulness during the day while promoting sleep onset and quality at night. Disruption of circadian timing has been consistently linked to mood instability, attentional deficits, and reduced cognitive performance, all factors that erode psychological confidence over time. Autonomic regulation further influences mental state through direct modulation of brainstem arousal systems. The vagus nerve, a key component of the parasympathetic nervous system, plays a central role in modulating heart rate variability, respiratory rhythm, and inflammatory tone. Techniques such as controlled diaphragmatic breathing, slow, paced respiration, and behavioral posture alignment provide somatic feedback that influences neural activity in cortical and subcortical regions involved in emotion regulation. Through consistent engagement with these physiological levers, individuals can exert top-down influence over internal states, promoting cognitive readiness and psychological stability even under demanding conditions.